Okay, allow me to share my screen. Okay, last Monday that is, we have discussed after your quiz trigonometric transformation, how we simplify complicated trigonometric functions when integrated using the trigonometric transformation technique. And we've only covered type 1, case 1, and case 2. So for this afternoon, we'll see if we can cover everything that is left, knowing that we have a lot of time to use up. That way, next week, we can have a new topic that is, I think if I'm not mistaken, techniques for handling inverse trigonometric functions. Okay, now for this afternoon class, we'll discuss type 2. Okay, so type 1 only deals with either the sine or the cosine function in your integral. So only one of these functions is present in the integral. Case 1 is for one which has an odd positive integer. Case 2 is for an even positive integer for the exponent of these two functions. Okay, so the two cases only differ with the trigonometric identities used. So in the case of case 1, we're using the identity sine squared x plus cosine squared x equal to 1. So we just transform it depending on our need to a particular identity, either the sine squared or the cosine squared. For case 2, the identity that is to be used when your n is even and positive is the double angle cosine equivalent of the sine squared and the cosine squared of x. Now, type 2 does not deal only with one of these two functions, sine and cosine, but this time we have a combination of the two. So we have also two cases in here. Okay, so let's look into the first case first. So case 1, if you're given an integral containing both the sine and the cosine, is when m or n is odd and positive. So either the exponent of the sine here or the cosine here, representing m and n respectively, are odd and positive. So let's say, for example, sine here is 7, and then cosine, the other exponent, is any real number. So for the other function that goes with the sine, it could be any real number. So m could be odd and positive. Okay, and the other could be any real number. It's the same thing with n. So n could be odd and positive, and n could be any real number. Now, what particular identity should be used? It's actually the same as the identity used in type 1, case 1. So the Pythagorean identity, sine squared plus cosine squared equal to 1. So whenever m or n is odd and positive and the other exponent is a real number, just deal with the exponent that is odd in the first place. So you see this one? Of the two functions, it's 3 that is odd and positive. This one is even. So what do we do with the function that is raised to an odd positive exponent? We take one function from it, or we subtract one from its exponent, and we set aside that function, and the remaining function, which is now even, is converted using the identity sine squared plus cosine squared equal to 1. That way it can be multiplied to the other function that is raised to a real number exponent, in the case of the cosine squared in here. So set aside one function from the function that is raised to an odd positive exponent, convert the remaining even exponent function to the equivalent of the other function which is raised to any real number exponent. So in this case, class, we set aside, so allow me to annotate, we set aside one sine function coming from the sine cube here. So this is the function already. Setting aside this function together with the differential of x. Now you have the sine squared here. The remaining part of the function, which is sine cube x, after you have taken the sine x. Now, since sine x is related to the cosine in a way that cosine is its derivative, or vice versa, cosine has the derivative sine, only that it's negative, then convert class this sine squared here using this identity 1 minus cosine squared x. Okay? After you have done that, multiply now or distribute the cosine squared x here, the function that is said to be raised to any real number exponent, and have it combined in the manner of multiplication to this identity, equivalent of the sine squared. So we multiply it, we distribute the cosine squared of x. The sine x dx, we don't do anything to it. Okay, we just simply set it aside. After doing that, you would see that you will have, for this one and this, you will have cosine squared x and of course the sine x dx. And for this cosine squared and this cosine squared, that would be cosine to the fourth of x, and still you have the sine x dx here. Now, if you look very closely to the two integrals that we have now, it can be dealt using power rule. Okay, your u in this case is the cosine of x. The du is the negative of sine x dx. Now, you already have the sine x dx here. All you have to do is place the negative sign. So if you multiply this by negative 1, then before the integral, there should be a negative 1. Now, what about these 2 and that 4? The 2 and the 4 are actually the exponents of your u here. So it's like you're dealing with these two integrals using the formula u raised to n du, yielding a u raised to n plus 1 over n plus 1. So power rule. And that's what's done here. Your cosine squared become cosine cube divided by 3. It's now negative because we need to place here negative 1. For the cosine to the fourth of x, it's now cosine to the fifth of x, or cosine x raised to 5 divided by 5. Since you introduce negative here, then this should be negative. Since this is negative, that makes it positive. And of course, you just affix the arbitrary constant of integration, c. So if you have both the sine and cosine function, please check first before you do any transformation of the two functions that are given in your original integral. Find one that is raised to an odd positive exponent. And then you split, you take out one function from that particular function which is an odd positive exponent and set it aside, just like what we're doing in here in the first example. The rest will be converting the remaining expression to the equivalent of the other function which is raised to any real number exponent. Do you have any question here? No question? Okay, so if there's none, we will continue with the second example. Now, you could see here that you have the square root of the sine of x, telling you that the sine of x is raised to 1/2. Okay, its exponent is 1/2. But this one is cosine cube x. So this is the function that is said to be raised to an odd positive exponent. This is the function that is said to be raised to any real number exponent. So for this function that is raised to an odd positive exponent, take out one function from it, and it should go together with the differential of x, just like what's done in here. Okay? What remains of the cosine cube of x is cosine squared x. Now, since these two are not the same functions and we're not to do anything about this, you convert the cosine squared of x into the sine function, or its equivalent identity having the sine function. That way you can combine it with the square root of the sine x here. Now, why would you do that? It's because the sine function has the derivative cosine. So this cosine of x dx that you have set aside will stand as the derivative of your sine x. So you could see here that the cosine squared of x is this one now. Okay, so it was changed using this one. After that, the square root of sine x is distributed. So you have here now square root of sine x, cosine of x dx. And then the square root of sine x times the sine squared of x will be sine of x raised to 2.5, or that would be 5/2. So the exponent is 5/2, and then you also have cosine of x here. So just like the previous treatment for the first example, your u here is the sine of x, your du is the cosine of x dx. The n depends on the n that you have here. So in this case, you have 1/2. The other n is 5/2. So using power rule, you only need to add 1 to these two n's. Now the resulting exponent of the function after you have added 1 to n is the same expression or the same number that you see in its denominator. So this is sine of 1/2 plus 1. So that would be 3/2 x divided by 3/2. So that is why you have here 2/3. This one, 5/2 plus 1, that would be 7/2. So sine of 7/2 x over 7/2. So now it became here 2/7. And still you have the arbitrary constant of integration, c. So transforming the integral having a combination of the sine and cosine in which one of them is raised to an odd positive exponent uses the identity of the sine squared x plus cosine squared x equal to 1. Just like case 1 of type 1, wherein you only are given one type of function, either a sine or a cosine only. Do you have any questions? Okay, so I think there's none. So I'll clear my markings. We'll proceed with case 2. This one, either m or n is odd and positive. Case 2, not either but both m and n are not odd but even. So both m and n are even positive integers. Okay, so positive integers. So what identity will you use? So it's similar to case 2 of type 1. You're going to use the double angle cosine equivalent of the sine squared of x and the cosine squared of x. So the same identity as case 2 of type 1. So here's the example that we have in here. So both the cosine and the sine are raised to even positive exponents. So either 2. So convert the cosine to this and convert the sine to this. So you have this one. If you multiply these two, the resulting denominator is 4. And the numerator will be 1 minus the cosine of 2x squared. Now, you see this? This is squared. Another positive even exponent. So this should be converted, class. This should be converted using the double angle cosine equivalent of the cosine squared of any angle. So if you will convert this to the double angle equivalent, the angle 2x here doubles. Okay, now let's see. So if you will distribute 1/4 here to 1 and this cosine squared of 2x and its equivalent, your first term will be 1/4 x. Okay, or 1/4 dx. The second term will be 1/4. This one, this is minus, so it's minus. And this converted to its equivalent double angle cosine. Okay? Double angle cosine is a plus between 1 and the cosine of the double angle. So you have 1 plus cosine of 4x. We double the 2x, it makes it 4x. Now, this 1/4 and this 1/2 becomes 1/8. And since this is minus, so you have here minus 1/8x. Now, let's go to this one. This will have 1/8 as well. So 1/4 times 1/2, negative 1/8. Because that's negative. Now, it's negative 1/8. However, class, if you integrate the cosine of 4x, this is comparable to the cosine of u du. The derivative of the u should be together with it or should be multiplied to it. That way you can answer a sine of 4x here. So in this case, since you only have 4, you only have dx here, you need to introduce the 4. The derivative of 4x is 4 dx. So you place here 1/4. That's the reason why, aside from the 1/8 here, you have 1/4. And then the integral of the cosine of 4x, which is the sine of 4x. Now, this is 1/4, this is 1/8. So actually, this can be simplified to 1/8x, 1/4 minus 1/8. So 1/8x minus 1/8 times 1/4. So that would be 1/32. Okay, 1/32. You have that one. So we'll just copy it. 1/32 sine of 4x plus c. Do you follow, class? Can you follow what's being done? You have any questions? Okay, there's none. Sige. So we'll continue, ha? Just ask questions if it's not clear. So we'll go to type 3. So we're done with functions that have the sine or the cosine alone and the one that has both the sine and the cosine. Both have two cases underneath, okay, under it. Now we go to type 3. So in here, we don't have cases anymore. So in here, it's specific that for this function, it's either you're just given a tangent or a cotangent where m is a positive integer. So no distinction whether m is positive and even or whether m is positive and odd. So whether it's odd or even, as long as it's positive, as it says here, it should be positive, then it's under type 3. Talking about a standalone function of the tangent and the cotangent. Now, what would you do if you're given such an integral? So you have now a new trigonometric identity. Actually, it's still coming from, or it's still derived from, the Pythagorean identity. The tangent squared equal to secant squared x minus 1. So actually, you only need this identity. I think it was shown to you also in your senior high. If you intend to have a second, then this one should be divided by the cosine. So you divide by the cosine squared of x, and you will have here 1 plus the tangent squared of x equal to the secant squared of x. If you wish to produce a cosecant, here you divide by the sine squared. So you're still using actually the Pythagorean identity. So you have 1 plus tangent squared x equal to the secant squared of x. If you wish to have only the tangent, then of course you transfer the 1 on the other side, giving you this one. Now, if it's the cotangent, so you will have, you divide by the sine squared, so you will have cotangent squared x plus 1 equal to the cosecant squared of x. Okay? That is if your division here is in terms of the sine squared of x. That would give you a 1 over sine squared of x, which is equivalent to the cosecant squared of x. Now, we go to the examples that's written here. So we'll go to them we'll check on them one by one. So example 1, cotangent of x raised to 4. So it's positive. So meaning, class, if it's your tangent or cotangent that is having a negative exponent, then you just have to invert it. What do you mean, Miss Ali? Just like this one. We cannot have a negative exponent. So for example, you're given the integral of tangent squared or negative, something like that. Let me erase this one. We'll write it properly. So you'll have, let's say, tangent of x raised to negative 2 dx. It's easy. This is like 1 over tangent squared of x dx, right? We cannot deal with the negative, so it's written like this. And what is this? That's cotangent squared of x dx. Convert it to the positive exponent because we are only given here a positive exponent for us to use in type 3. Okay? So that's how you deal if you're given a negative exponent, convert it to positive. So in here, you have cotangent to the fourth x. So split it into 2 cotangent squared x. Now, since you need a derivative for the cotangent, that way you can use power rule for it. Then you use the identity, the equivalent identity for the cotangent. What is that? This is it. Cotangent squared x is cosecant. By the way, class, this is 2. Cosecant squared x minus 1. There's a typo error. So cosecant squared x minus 1. You convert the cotangent here to cosecant squared x minus 1. Then have the, use another color, then have the cotangent here distributed. Okay, so your first integral will be cotangent squared x, cosecant squared x dx after you have multiplied it with this. The next one is cotangent squared x dx when you have multiplied it to negative 1. Now for this one, for the cotangent squared of x, cosecant squared of x dx, it's the same as the previous examples given to you. Okay, your u is your cotangent of x. In this case, your n is 2. Your du is negative cosecant squared of x dx. So in here, you already have the cosecant squared of x dx. So you only need the negative sign. So negative there and negative here, that makes it negative 1/3 cotangent cube x. Because we used power rule for the cotangent of x raised to 2. Because this is already its derivative. So power rule for that. Whereas this one cannot still be integrated, class. You convert it again to its equivalent identity, which is cosecant squared x minus 1. You already have an answer for the first term, but there's a need for you to convert here the cotangent to cosecant squared x. So it's minus cosecant squared x minus 1. Now, you copy your answer here. The answer for the negative cosecant squared x dx is cotangent x. It's a basic trigonometric integral. And this one, negative, negative, it's positive. So plus x, because this one would simply be a dx. Okay? So you have here the answer now for sample number 1. The first one made use of power rule. The second term made use of simple trigonometric integral, and the third made use of the integral of the differential of x, which is simply x itself. So that's under module 1, the basic concepts of integration. Any question with number 1? Any question with sample 1? Okay, so there's none. So I'll go to number 2. So tangent cube of x, we split it. One is tangent x, and then another one is tangent squared x dx. So in here, you could see that your tangent can have the derivative secant squared x. So you need to convert this tangent squared of x to secant squared of x minus 1. So the identity that was discussed a few minutes ago. Then distribute. Then process. So you have tangent secant squared x. This again is your du. This is your u raised to n. Your n being 1, so when you use power rule, that would be tangent squared x over 2. And for the tangent here, class, there's no direct integral for the tangent of x. Why? We need to convert this. The tangent of x, this was shown to you already, in the previous example can be written as the sine of x over the cosine of x dx. Now, if your u is the cosine of x, its du is the negative sine of x dx. Now, so you lock here the negative and you place here negative. This is the form of du over u yielding an ln of u, as discussed under the topic. Your u is in the denominator, your du is in the numerator. So then the answer is ln of u. So our u is cosine. So the ln of cosine of x, it's negative because of this. And since it's negative in here, that makes it positive. So your answer here for the first term, which is 1/2 tangent squared x, is just added to the answer for the second term, which is the ln of the cosine of x. Now, there's a note here that tangent of x, secant squared of x dx, can also be, after this one, where is it? Oh, wait, plus. This one, after this particular, shall I say, multiplication of the tangent of x to the identity here, you will have tangent of x, secant squared of x dx. You can split it class actually. Pwede siya ma-split ang tangent squared mo, nga ini, into secant, or rather, a secant squared function here to secant x. So you will have secant x multiplied to secant x tangent x. This is your u raised to n, and this is the du. If your u is secant of x, the derivative of that is tangent x secant x dx. So it could also be that instead of answering here tangent squared x over 2, you can also answer secant squared x over 2. Because this u here, which is the secant of x, has the exponent of 1. So if you use power rule to it, that would be secant of x squared over 2. This tangent x secant x dx is the entire du of your u, which is secant. So you have two possible answer class for this particular integral. You can have this. You can also have this one. Both are correct. Both are acceptable. So the other one, use the tangent as the u, the first one. The second one, use the secant of x as the u. Split niya pa ang secant squared x here to secant x to come up with this expression. Do you have any questions? Do you follow so far? Okay, so no questions. So I will continue. Miss Ali will continue if there aren't any questions. Okay, we go to type 4. This one is a standalone tangent and cotangent, that just like type 1, which is a standalone sine or cosine function. Type 4 now constitutes of the combination not of the tangent and the cotangent, but rather the tangent and the secant, or the cotangent and the cosecant. Okay? The secant, remember, the secant is the derivative of the tangent. So secant squared is derivative of tangent. And cosecant squared x negative of that is the derivative of the cotangent. So that's under type 4. And in here, we have two cases. Okay, one is when m is odd and positive, n is any real number. And another one is when n is even and positive. This one, the derivative itself is even and positive, not odd. And m is any real number. So we'll look into each of the cases here one by one. Okay? Now, if m is odd and positive, and the n, which is the secant, in the case of the tangent, or the cosecant in terms of the cotangent, is any real number, you have to split, class, the tangent of mx secant of nx into tangent of m minus 1x secant of n minus 1x and tangent x secant x. Now, simply put, I'd like to simplify this one. Whenever the exponent of the m is odd and positive and n is any real number, for both of these cases, you just simply take one tangent and secant from each. So in the case of the tangent x secant x function, get one from each. In the case of the cotangent and the cosecant, get one from each. Then look at the remaining trigonometric expression. Remember that when you take a secant and tangent x here, class, you are having in mind that you have a second function because the tangent x secant x is the derivative of the secant. That's the same thing in here when we talk about the cotangent and the cosecant function. Once you take one cotangent and cosecant from this particular combination of cotangent and cosecant, that already represents the derivative of the cosecant. So what does this tell you? Or if you are to critically think, it tells you that if you intend to use the tangent secant, tangent x secant x dx derivative, whatever is the remaining tangent function there, you are to convert in the identity secant squared x minus 1. It's the same thing with the cotangent. You are to convert it to cosecant squared x minus 1. That way, all in all, when you now multiply, you will have a remaining main function of secant and a remaining function which is a cosecant. Which will you pair with the tangent secant and the cotangent cosecant. Now, I think that would be difficult if I would just simply explain here. So it would be concrete if we have examples. So look at here. M is any positive odd exponent. Okay. N is any real number. So this is your N. It's the secant that is the n. It's the cosecant in the case of the cotangent that is raised to the n. So the exponent of the tangent and the cotangent is m. Here, class. So the tangent and the cotangent is raised to m. The secant and the cosecant is raised to n. So just take one from each. Okay. In here, however, the examples are all tangent secant combination. So you take one from each. You took one, and that particular second tangent which you took is already here. So tangent will now be tangent squared x, your original tangent cube of x, and your second x raised to 5 becomes second x raised to 4. You don't have any problem with this because it's second already, and this is its derivative. Your challenge is the tangent, so convert it in terms of second. That way you will have one second function. So converting the tangent squared of x to the second will use the identity secant squared x minus 1. This was just copied again. And this one is just there. It's copied as well. Next thing you do is you distribute. So distribute or multiply the secant squared x minus 1 to secant x raised to 4. This would be secant x raised to 6. This is still the derivative intact. And you have your second to the 4th. This is still the derivative intact. Then you can use power rule for this and this. This becomes 7. This becomes 5. Why? Because this one stands for the derivative of the second. Now in here, it's the same thing actually. Same thing here. You take one tangent and take one secant here. It's okay. So you have this tangent second. Okay. Now, since you took one tangent here, that becomes tangent squared. Since you took one secant here, it would be secant of x raised to negative 1/2 because this is 1/2 actually. Minus 1, that would be negative 1/2. This is the negative 1/2 expression. Secant of x raised to negative 1/2. 1/2 over 1. I'm referring to the exponents of the second function. There should be an x here. Okay, so that would be second of x raised to negative 1/2. No worries because I still need to convert the tangent squared x here to the second squared x minus 1. So this is it. This one is just the second of x raised to negative 1/2. Here it is. Okay? This one is still the set aside tangent x second x, which will stand for the derivative of the second. Then just do your algebra. Multiply. 2 minus 1/2 is 1.5, and that's 3/2. This is still your derivative. And this is still negative 1/2 because you're just simply multiplying it to negative 1. This is still the derivative. So power rule for the second function. So if you use power rule, this 3/2 plus 1 becomes 5/2 over 5/2. So that's 2/5. This is negative 1/2 plus 1 is 1/2 over 1/2. That is what you see here at 2. Here at 2/5. Okay. So always take one tangent and one secant from the tangent secant combination, or take one cotangent of x and cosecant of x from the cotangent cosecant combination. The only restriction here is that's very important, that the m, the exponent of the tangent or the cotangent, should be odd and positive. That's your case 1. Odd and positive, where n is any real number. Any question? There's none? Okay. I will clear my markings. We'll proceed. Now, case 2. N is an even positive integer. So ano si n? N is the exponent of the secant and the cosecant. So it's even, positive. And this time, it's the m, which is a real number. What do? Use the substitution, the trigonometric substitution, secant squared of x equal to tangent squared of x plus 1. And you split. You split your secant of m, or rather your secant of x raised to m into, look at this. This is very important because this is new. This is a new technique here. From the secant and the cosecant, which is raised to an even positive exponent, you don't subtract one only. You don't set aside only a secant or a cosecant. You set aside a secant squared or a cosecant squared. You subtract 2 from the exponent of the original second function. So we're used to subtracting only 1, right? From all the techniques, whether we're talking about type 1, type 2, and type 3. In here, we subtract 2. We do the same if we're dealing with the cosecant. The purpose, class, is, of course, I think you have already the idea. Why take away a secant squared or a cosecant squared from a second function? It has a purpose. It will have to be, that particular secant or that particular cosecant will have to be, shall I say, representing the derivative of the remaining functions that you have. It will be illustrated here below. So the secant squared that you set aside, or the cosecant squared that you set aside, you took from the original function secant and cosecant, excuse me, will stand as the derivative of the remaining functions there, as long as you make them into one single function, which has a derivative of the secant squared of x or the cosecant squared of x. Allow me to erase first so that it would be clearer, and then we go to the example. This is your n. This is your m. So according to the instruction here, your m, the m will be you're going to get 2 from the not the m, but rather the n. You subtract 2 from the n, in this case here. Okay, so now your cotangent, this is your cotangent, nothing happened to it. We just copy it. For your cosecant, you split it into 2. So since this is 4, the reason why it has to be even and positive, that's the requirement there a while ago. So I cannot scroll up because I'm already in the annotation mode. So you split it into 2. So you have this one and this one. The other one you set aside. It's already the derivative of something, whatever that something is. Now, this cotangent that you have here, this is your m, any real number, you don't do anything to it. You need to convert the cosecant squared of 2x here to cotangent squared of 2x plus 1. That's its identity. That way, when you distribute, you only have one homogeneous function, the cotangent of x and another cotangent in here. So you have your cotangent to the fourth of 2x. I think this one, the cotangent to the fourth is for the 1. And this one is cotangent to the sixth of 2x. It's the second term in here. Now interchange anyway, the derivative is still well placed. Okay. If you look very closely, class, if you look very closely, you have added the constant 2 in here. You have the constant 2 in here. Why? Your u, in this case, is cotangent of 2x. So the n in the first one is 4. The n in the second one is 6. The du of that, using chain rule, is negative cosecant squared of 2x times 2 dx. So that's the reason why there's a need for the multiplication of 2 here. And there's now a 1/2 before each integrals. That's the purpose. You multiply the 2 integrals actually by 2/2 because you need the 2 in here in the derivative. Now in here, your n is 4. So if you use power rule, you will have cotangent of 2x raised to 5/5. The reason why you have the negative in here because the derivative is negative. So this one here is positive. So it's negative and this is the 1/2 here. The other one is still the same. Your cotangent 2x raised to 7. There should be a 7 here. Divided by 7. And it's a negative. The negative is already in here and that's your 1/2. So if you will simplify, you will have negative 2/5 cotangent of 2x raised to 5. And for this one, you have negative 1/14. 1/2 and 1/7 is negative 1/14. Cotangent of 2x raised to 7 plus c. Now in here, in here, the requirement is this. N is even and positive. M is any real number. Go back. This is your M, which is any real number. And this is your N, which should be. So this is the limiting condition here, which should be positive and even because you need to split it. You need to set aside. There shouldn't be any 2, by the way, in here. There should not be any 2. You need to set aside the cosecant squared of 2x in here for the derivative of the cotangent. Do you get it? Class, you're very quiet. So I only have 2 line of thinking here. Either you fully understand or you don't follow anything at all. So let me help you. If you don't understand, you ask question. Because I am simply tasked to cover everything that I need to cover. I need to discuss everything that is included in the syllabus. So no topic here remaining undiscussed if that is the case. And it would be a bit of a challenge later on when you are given already a mix of this. What do I mean by that? It's already not classified as type 1, type 2, type 3, type 4, type 5, type 6. It's just given to you as is. So that's where the challenge is, because you have to think what particular type is this and what identity will I use. That way I correctly transform it and get the correct answer for the evaluation of the integral. So now I'm asking again, do you have any questions? No question? Okay, so then it's clear. We'll erase this one. We'll finish everything here. That way next week we can go to the next topic. And you can have a longer quiz for trigonometric transformation on Monday. Okay, now here, type 5. Okay, we already have type 3 and 4. Type 3 is either tangent or cotangent. Type 4 is a combination of tangent second and cotangent cosecond. Now, type 5 is a standalone function again. Second or cosecond only raised to n. There is a limiting condition here, meaning class, this is the condition that has to be met. That way you can use the technique here that is presented. N has to be even and positive. Why do you think n should be even and positive in the first place before I discuss? What's the purpose that, why is it limited to only the condition that n should be even and positive? What do you think is the reasoning behind? Okay, so that this will not be a monologue, let me ask. Drews, why do you think it's limited only to n, which is positive and even? Are you there, Drews? Aujero?
Yes, miss.
Okay, why do you think? Do you have any idea why n should be even and positive? Hindi pwede positive and odd. Meaning even din siya dapat. Why do you think should be even? And
Para magamit yung sa
para? What do you think?
magamit siya miss sa o ganito.
Actually, it's in here. The question, the answer to my question in here. It's in here.
Para magamit siya sa Pythagorean Identity.
Para magamit siya sa Pythagorean Identity. What you are converting actually is the second squared of x to tangent squared of x plus 1. Okay? We know for one that if we already converted the second squared of x to 1 plus tangent squared of x, the only way that we can integrate these two terms here, the 1 and the tangent squared of x, is for it to be multiplied to the second squared of x, not just second of x. Because the second squared of x is the derivative of the tangent squared of x. Stand alone, your second squared of x is also integrated right away using the simple trigonometric integral formula. So that's the purpose why it has to be really even. Because the other expression, you convert to the tangent, the other one that is squared, because you're going to get 2 from it, is the derivative of that expression, which is in terms of the tangent. Just like the way you could see here in the example. So it's second to the fourth of x dx. It was split into second squared of x, and just take this one, it was double type, and another second squared of x dx here. This one is already kept class. We don't do anything to this because that's already the derivative of this transform second squared of x, which is what? The transformed second squared of x is the tangent squared of x plus 1, which is its equivalent identity. If you're going to distribute the second squared of x dx to these two, they are readily integrable. The first integral will have the tangent squared of x times the second squared of x dx. This is u raised to n du. So you use power rule. For the second one, even easier, because the second squared of x dx is right away integrable using the simple trigonometric integral. The answer is the tangent. So that's the purpose why in type 5, your second or your cosecant function should be raised to an even positive exponent. The second squared and the cosecant squared, as I've said already, I think for the third time, will be set aside to represent the derivative of the tangent and the cotangent respectively. So they have to be converted to the tangent and the cotangent. That way the second squared, or rather the cosecant squared and the second squared will be their derivatives, and you can readily use power rule. Hi? Any question here? The last one is even easier. This actually, the last one is the easiest of all trigonometric transformations. That is why it's discussed last, because it's easiest. You start with the complicated, that way comes the last easy na siya, hapos na siya intindihan. Any question? Okay, I will clear my markings here. I go to type 6. No cases underneath because we have, I think you were given this identity already in senior high. You have a combination here, class, of the sine and cosine. They differ with type 2 because we also have type 2, right? The sine and cosine. The number one difference with type 2 sine and cosine combination is that they are raised to exponents. In here, your sine and cosine are not raised to exponents other than 1. So both are having exponents 1. The only challenge here is that the angles are not the same. Let's say this is sine x, this one is cosine 2x. If this is sine of 5x, this one is sine of 2x, or cosine of 3x and cosine of x, something like that. In our vernacular language, hindi sila pareho, theta. So what would you do? Because if they could be represented by just one function, then right away you can use the basic trigonometric integrals, relying only on the formula of the sine and cosine. And it's in here, class. If you have a combination of sine and cosine which have different angles, you convert it to this expression. It's 1/2 the sine of, you take the sum of these two. If this is x and this is 2x, this becomes 3. By the way, there should be an x here. X also. So sine here, where you add, and then this one is you subtract the m and the n. If it's both cosine having different angles, this is the formula. So the first cosine is addition, the second cosine is subtraction. Okay, this is both cosine. The last one is both sine. So both for sine, you have here the only difference rather of this formula from the one on top for cosines of different angles is it's negative, and instead of a plus here, it's minus. But in terms of what you do with the angles, it's the same for the first and the second term. In here, you add the angles. In here, you subtract. In here, you subtract the cosines. In here, you add. Okay? So if you have both cosine or both sines having different angles, your equivalent identity is a cosine. So cosine siya. But if you have a combination of a sine and cosine, your equivalent identity is a sine. A sine of two functions. Okay? Both having 1/2 as the constant multiplied to it. Very easy. This is the easiest of all trigonometric transformation. Take a look at this one, sine and cosine. Okay, different angles. So what you do, in the first formula, you add the angles. So 3x plus 2x. In here, you subtract 3x minus 2x. So your integral will be, for the first one, is 1/2 integral of sine 5x. In here, you have sine x. You can readily integrate this and this. You only place 5 in the dx because the derivative of your theta here or your u is 5 dx. So you will have to multiply your 1/2 here by 1/5. So you have 1/5. Integral of the sine is negative cosine 5x. This one is standalone. So the integral of that is negative cosine. This is your 1/2 multiplier. So you place here only a bracket. Now, in here, another cosine and sine, it's just the same. Wait, cosine na siya, no? Probably this is plus and this is minus. So this is sine. Okay. In here, it falls under this one. Okay? This one is a combination of sine and cosine. This one is here. Same function, different angles. The negative 1/2, the cosine of 3x plus 2x minus the cosine of 3x minus 2x. So negative 1/2 integral of cosine 5x. This one is minus cosine of x. So you need here another 5 and you have 1/5. So 1/5 sine of 5x. The integral of cosine here is sine. So it's negative because we have negative in here. That's it. Very, very simple. You just need to add the angles or subtract the angles and recall this identity. Okay? Another one here is we have now the second type, cosine. The cosine of two different angles. So you only need to add here and it's positive 1/2. So 1/2 cosine plus cosine minus 1/2 cosine of 5x and this one is cosine of x. Then integrate this. So you have 1/2 times the quantity 1/5 sine of 5x here, and you have here sine of x. Okay? Now there's a note that you can also process this one, the cosine of 3x, cosine of 2x in this way. Sulit siya. You can interchange actually. The cosine of 2x is written first and then followed by the cosine of 3x, meaning your m is 2 and your n is 3. Doesn't matter, class. So look at it. It's 2x plus 3x and 2x minus 3x. So this one is cosine of 5x and this one is the cosine of negative x. What's the integral of the cosine of negative x? Your angle now is negative and as such its derivative is negative dx. Okay? So you have now 1/2 cosine of 5x and you have this one, though its derivative is negative dx. In your trigonometry then class, how do we measure angles, by the way? If you can still remember. How do we measure the angles? Is it clockwise or counterclockwise? Are you still there? How do you measure angles? Clockwise or counterclockwise for it to be positive? Marion, when is an angle positive and when is it negative? Okay, thank you for those who answered in the chat box. Thank you, Kyle and Carlos. Correct, very good. If you measure it counterclockwise, it's positive. If you measure it clockwise, it's negative. So look at me here. If I measure, kindly mute yourself. Kindly mute yourself. Thank you. Can you please that? Let me check. Please.
¿Estás? Yo.
Thank you. Now, if you measure angle counterclockwise, it's like this. This is cosine of 180 degrees. Its answer is -1, right? Positive 180 degrees because it's counterclockwise. If you measure it clockwise, it's cosine of -180 degrees because we measured it clockwise. Still, the answer is -1. So whether you have a cosine of theta and a cosine of negative theta, the cosine of these two angles are the same. So you can see here that the cosine of negative x is just the cosine of x. No need for you to place the derivative of the angle here, which is -x to -dx. Although mathematically, if you do that, that is still correct. Okay? So if you process the integral, it's the same. So the derivative of the cosine is the sine of 5x, and you have here 1/5. And the integral, rather, not the derivative, the integral of the cosine here is also sine x. Note that this is the same result as the previous one. Whether this is m and this is n, or this time this is n and this is m, the answer is still the same. I hope you get it. So either you treat one as m or the other one as n, or vice versa, you will still be getting the same answer. We'll end with this fourth example. You have here the cosine of x and the cosine of 2x and the cosine of 3x. I'm sure if you look at this and you did not know this set of identities, you will right away be very nervous, or you will rattle, as the term of the students then, because it seems like very complicated already. You just process it piece by piece. Okay, so you process this first, this one. So you have 1/2 the cosine of 3x plus the cosine of x. Where is this coming from? By the way, class, let me annotate. The cosine of 3x here, you kept it. Okay, you kept it. You only first process this 2. How did you process the cosine of x and the cosine of 2x? You process it using the formula that you have above. And that is, if you have the cosine of two angles, that would be the sum of the two angles for the first cosine and the difference of the two angles for the second. Both are being added. Okay, so amo na siyang natabo. Why you have this one? You have already the answer cosine of 3x plus cosine of 2x. Okay, you have 1/2 integral of cosine 3x plus cosine of x. This one, I will annotate again. This one now, different color na lang. This one is for this, using the set of identities on top. The one that I placed on the red box is still intact. We have the cosine of 3x in here. The goodness about this class is this. I'll use another color. You have a cosine of 3x here and a cosine of 3x. You can see that here. Okay. So what's done here is you distribute the cosine of 3x as a multiplier to these two. So you have the cosine of 3x squared. For the second one, you have the cosine of 3x and the cosine of x. Now this one is a cosine raised to an even exponent. So this is type 1, case 2. Standalone cosine raised to an even exponent. You need to convert it using the double angle cosine equivalent. Type 1, case 2. So you double the angle. So you can see it here. It now became 6. And it's 1 plus cosine of 6 over 2. This one is the identity for the cosine 3x squared. What about this? You will use again the identity that was shown to you on top. The cosine of the 2 cosine with different angles. So you add the 2, that would be cosine of 4x, and you subtract, that would be the cosine of 2x here. And it's still 1/2 here. So you have 1/2 written before the integral. And by the way, wait, half. So the entire thing is 1/2. So there should be class. There's a typo here again. There should be another 1/2 here. This because converting this to using the identity on top will need a 1/2. Okay. And if you're now going to process this, you will have 1/4 x. This one will need a 6 dx. So you need to have 1/6 multiplied to 1/4. So that's 1/24 sine of 6x. For this one, this will need a 2. So you'll have 1/2 times 1/2 times 1/2. So that's 1/8. So nalipatan lang pag-type 3 ang 1/2. So 1/8 sine of 2x. For the cosine, you will have 4. So meaning your 1/4 times 1/4, that's 1/16 sine of 4x plus 3. So that's it. You have here 3 functions and how it was processed using this technique in here. Okay, but there are expressions also, class, na you have 3 and cannot be processed like this. So you just have to find a way, that way the resulting angle of your cosine, or it could be your sine, can be multiplied to the remaining angle which you have set aside. Just like in this case, so you have a cosine of 3x. When you process the first 2, it resulted also to a cosine of 3x. So good, because when you multiply these 2, you will just simply add exponents and use the other trigonometric transformation available for you to use. So remember, in here in sample 4, you did not only use 1 transformation, you used 2 transformation. 1 here and 1 in here for the double angle. Actually, you have several transformations in one example only. So integrals can be as complicated as this, or it could be as simple as the one that you have in the previous examples, wherein you only have one single trigonometric expression to process or to integrate. I suggest that when you have your free time already, since what is written only in your asynchronous class is just the 3 hours, the 1 hour is for your asynchronous, and we don't use it in answering or in practicing solving the examples here or the practice exercises in your Canvas, and in processing your problem set. That way, you are already preparing for the quiz. You need not wait for me to say that there's a quiz for you to prepare. Any questions? It's 4:19. I'm sure you're very tired mentally. You have chosen a profession that is not easy. If it's easy, it's not CHE. It could be easy probably in other schools, but not in USNS. Do you have any questions, class? There's none? Okay, I'll stop sharing. Monday next week, so I'll stop sharing.